Okay, we're all set. I'm going to turn it over to you, Greg. Welcome, everyone.
Sounds good. Yeah, welcome everybody. We are going to do a presentation on ultraviolet disinfection today, and we're going to call that Shining a Light on UV Disinfection Best Practices. I am Greg Manier. I'm a business developer for Xylem Water Technologies. I got my start here about 12 years ago through our company ETS UV. Consider, I guess, myself a technical expert in ultraviolet disinfection, mainly focusing on UV manufacturing, commissioning, integration, maintenance, repair, system sizing and implementation in commercial aquatics applications. 10 plus years of experience in these industries. We've been installing, commissioning, working on UV disinfection equipment around commercial aquatics throughout North America and beyond. In addition to all of that, I've got a lot of experience with our equipment in other industries as well, from municipal wastewater, drinking water, food and beverage, pharmaceutical applications, oil and gas, offshore, you name it. We use UV quite a few different places. So, skipped ahead a few there. So the agenda for today, basically want to talk about how UV works. We want to talk about system sizing and UV transmittance, or UVT. We're going to talk about the difference between low pressure and medium pressure UV systems, indoor and outdoor applications, and the water and air quality implications that are there. And we're going to touch base on NSF certification and how it specifically relates to UV, and then give you guys a glimpse of a case study that we have. Quick update too. So I've got a lot of different questions around our company. I'm reporting from Xylem today. Xylem has recently acquired Evoqua Water Technologies, which had owned Neptune Benson and ETS UV. The acquisition took place in May of 2023. So Evoqua Water Technologies got bought by the company. Got over 100 years of innovation and service to our customers with leading brands. We do have about 5,100 different patents and trademarks throughout the company, about 23,000 employees globally. We operate in 150 different countries, and we have over 350 locations around the world. So we went from some humble beginnings up to a large acquisition here that, gets us in front of a lot of people with our solutions. So first section, and jump right into it, talk about how UV works. And to start it off, we have a poll question. So I'm going to go ahead and launch that poll. Yeah, hopefully you guys can see that up there. But basically the question is, do you currently have UV at your swim school facility? Easy yes or no. We'll leave that one open for a little bit. See, we've got quite a few that have it, some that don't. So hopefully we can enlighten both sides here. So talking about how UV works. First, we have the spectrum of light. So UV in the electromagnetic spectrum. Essentially what we're looking at, is the ultraviolet portion of the UV or the spectrum, the visible portion and the infrared portion. UV disinfection predominantly takes place in the ultraviolet portion of the electromagnetic spectrum, specifically in the UVC portion, where we operate around 200 to 280 nanometers. Talking about UV applications in the water and how it actually does its work, two main components to using UV to treat water. One, inactivation of microorganisms. So basically the photons are absorbed by DNA in the microorganisms, and it leads to the inactivation of the microorganism. It basically affects its ability to replicate, so it makes it non-viable. And it does this by altering the thymine base of the units, or the base units in the DNA itself. So essentially it's damaging the DNA, in the microorganism to a point where, again, it cannot replicate. The other use for UV, photochemistry. So we're using photons of UV light, and they're absorbed by molecules such as ozone, total organic carbons, chloramines, and it leads to a chemical change resulting in their destruction. So specifically how those two apply to swimming pools, two main functions, disinfection and chloramine reduction. So disinfection, basically the UV is going to complement your primary chemical program. It's not intended to replace it, but it complements it, and it does so to an extent where it can reduce demand and usage on your chemicals. We inactivate bacteria and microorganisms that are responsible for various recreational water illnesses, or we call them RWIs, such as chlorine-resistant cryptosporidium. And we'll touch base on this a little bit later further. As far as the photochemical reactions, predominantly in aquatics, we're talking about chloramine reduction. So essentially, we have our free chlorine that we use for disinfection, and that reacts with organic compounds in the water. When it does that, it forms disinfection byproducts, or DBPs. For the most part, chloramines is what we were worried about, mono, di, and trichloramines. The chloramines can be volatile, they'll off gas, and essentially, they do concentrate at the water and air interface. These chloramines can cause different things, mainly what's noticeable, and a tangible feeling thing we can get in the environment. It's going to be burning, red eyes. You get that nasty chlorine smell that we get. Can cause respiratory issues. So that can dissipate into the natatorium as well, and it can cause corrosion. It's responsible for the offensive pool smell, as we've talked about. So UV energy essentially dissociates the chloramine molecules, and it reduces them to their basic elements. So it breaks apart the chemical bonds of the chloramine and reduces them to their basic elements. We'll talk a little bit about system sizing, UV, why we look at UV transmittance. We've got another poll here for everybody. We'll go ahead and launch that. So basically, what type of UV system do you have if you have one? Low pressure, medium pressure, or not sure? All right. Some interesting results there too. We've got a couple not sure, so I'm really excited to kind of show you guys the difference between those. So essentially, the main goal of a UV disinfection system is to apply a dose of UV light to the water. A dose is a measurement of UV intensity over time. So essentially, we have the time of exposure, and generically on UV systems used in commercial aquatics applications, we're using a kind of a dummy flow rate or a fixed flow rate. So this is essentially going to be the peak flow rate for the design of the system itself, for your water circulation system. Basically, contact times 1 over flow rate. Generically, what that translates into and how flow applies to the dose itself. If we have half of the flow, we pretty much get double the dose. It's inversive. The other side of the dose itself is the lamp output measured through the water. So that's the UV photon energy. And we call that UV intensity. So usually UV intensity is measured either in milliwatts per centimeter squared or in watts per meter squared. And it's subject to a few different things: lamp power, the size of the lamp that's used in the system, the output of the lamp itself, and it can change due to water quality and system cleanliness. So when we take both of them, put it together, UV dose is subject to changes in flow rate and UV intensity. So a couple more points to hit on. Flow and dose are inversive. So essentially, the slower the water is moving through the UV reactor, the more contact time we have with it. It's kind of like putting a pot of water on the stove. The longer you leave it there, the hotter it's going to get. So the slower the water is moving through the UV reaction chamber, the higher the UV dose that is going to be applied to the water. UV intensity, though, and dose are pretty much proportional. If your UV intensity increases, your UV dose will increase as well. If it decreases, due to fouling of the system, turning the lamp power down, any of those situations, your UV dose will also drop. So what is ultraviolet transmittance, or UVT? So when we talk about water quality with UV systems, we're not talking about, the main water quality points that everybody looks at in their pools, from pH, total chlorine, different things along those lines. What we're talking about is strictly UVT. UVT is a measurement of the amount of light that penetrates through the water. 0 to 100% is the scale. 100 is the highest, and it's tested with a spectrophotometer in either a 10 millimeter or a 40 millimeter sample cell. So what we're doing, if you can see the graphic in the center, is we're filling up the sample cell with the water. We're passing a UV light source through it, and we are reading how much light has come through it on the other side with a UV sensor. So again, as your UV intensity increases, or your UV transmittance increases, your UV sensor on the other side will pick up more of a return, and it will interpret a higher UV transmittance. So it's easier to push that light through the water. Talking about lamp output for UVT. So lower UVT limits the performance of the UV lamp itself. A UV lamp has a finite amount of energy. It can only put out what it can put out. So essentially, UVT is important for this sizing parameter, just because we need to understand that in the water before we can make a size based off of flow rate alone. A lot of times when we look at UV systems and we try to determine exactly which one is applicable to the application, it's very simple. We say, well, what's the maximum flow rate this system can handle? 1,000 GPM. Okay, my body of water is 800. It fits within there. But what does 1,000 GPM represent? And it represents, the maximum flow rate that can treat at a set UVT. So put that all into context here. Systems are designed, for high efficiency at high UVT. They can be really ineffective at lower UVT levels. So if you look at the graphic in the middle, the yellow dot is essentially looking down the end of a single-ended UV reactor. That is the lamp. The UVC energy is radiating from the lamp. That's the red. And we're trying to get all the way to the outside wall of the UV reactor. That's always the goal. We don't want any untreated water passing through the reactor. So how UVT plays into this, as the UVT decreases, it's harder to push the water, or the light through the water, all the way to the outside wall of the UV reactor. As the UVT increases, the light travels easier through the water, and we treat more of the water with it. This graph here basically is considering the fact that we want to maintain a static UV dose. So if we're talking about disinfection, that UV dose is usually around 40 millijoules per centimeter squared. And what we're saying here is at the UVT of 99%, we're able to maintain a UV dose of 40 millijoules per centimeter squared at a maximum flow of about 250 GPM. Now we can see here, as the UVT degrades, the maximum flow rate also drops significantly while maintaining that same UV dose of 40 millijoules. It's so substantial, looking at a 5% drop from 99 down to 94 or so, we lose almost 40% of the system capacity in just that amount of UVT drop. So it's not necessarily a linear measurement. As your UVT goes, we lose one millijoule of dose. It doesn't necessarily work that way. But it does have some pretty big implications to system sizing itself. Talking a little bit about what the Model Aquatic Health Code says about it. There's a lot of words here, but essentially what's mentioned in there is when you're considering sizing UV systems, you want to ensure that they're sized with a UVT of around 94% or lower. Just because you saw from the previous graph, if we start to size systems that are based on a water transmittance that's extremely high, it might not have enough power to do the work, in the actual application. So, and I'm sure there might be some questions on what standard UVTs are in aquatics facilities. Generally, 94 is pretty much the benchmark for it. It's very rare that we would see facilities 95 and better, based off of, a lot of experience in the field. And this generally changes by pool type itself. If it's a competition pool that doesn't get a ton of use and there's, just athletic bathers in there, for swim competitions, generally the UVT can be higher in those. Activity pools or outdoor splash pads or things like that, the UVT is generally a bit lower, in the 88 to 92 range or so. So they all vary based off of the pool itself. So moving on from UVT, I'm going to talk about the difference between low and medium pressure systems. So when we talk about pressure, a lot of people assume that we're talking about the water pressure that's inside of the reactor itself. The pressure referred to here is basically the pressure of the mercury gas inside of the UV lamp. So as that pressure changes, it changes the wavelengths of light that are produced. So essentially, if we talk back to the original slide here on the electromagnetic spectrum, and we're looking at the ultraviolet portion of that spectrum, we are in the UVC again, and we're talking about 200 to 280 nanometers of output. So the two main types of UV systems that are in the market, low pressure and medium pressure. And we'll talk about low pressure first. Low pressure basically has a higher electrical efficiency than medium pressure lamps. They're generally low wattage, maybe a maximum of 200 watts each, anywhere from 100 to 200 usually. They are monochromatic, meaning they only emit a single energy wave from this 200 to 280 range. They operate on 254 nanometers specifically. And that output is primarily used for disinfection applications. They do have some other advantages. They can break down monochloramine, but they do not have much success with di and trichloramines. Some differences in the systems, they are generally larger. The lamps themselves are longer than a medium pressure lamp, and due to the lower wattage of the lamp, you generally need more lamps to achieve the same output that you would get from a medium pressure system. So moving on to medium pressure UV, much lower electrical efficiency than low pressure lamps. Some of the smallest medium pressure lamps in the field are about 1 kilowatt. This is about 1,000 watts of output in comparison to the 200 watt low pressure lamps. Any medium pressure lamps that get smaller than about 1 kilowatt, the power density of the lamp is usually too high to make them efficient. So that's pretty much where medium pressure systems start, 1 kilowatt and up. Some of the big differences with medium pressure is the polychromatic output versus the monochromatic output from the low pressure systems. Polychromatic meaning we have all different outputs from 200 to 280 nanometers and even beyond that. But essentially, as far as the work that we're trying to do in the water, what's between 2 and 280 is what's beneficial to us. Being polychromatic and having more outputs, we have the ability to demonstrate with medium pressure systems a higher germicidal disinfection efficiency. With all of these different wavelengths that are emitted from the lamps, they can do more damage to the DNA and the RNA of the microorganisms. And sometimes a lower UV dose from a medium pressure system can accomplish the same, that the standard dose from a low pressure can accomplish. The other advantages to having the polychromatic output is that medium pressure UV lamps are good at breaking down all 3 chloramine species. So not just the monochloramines that low pressure can handle, this also focuses on the di and trichloramines. They also have a very small footprint and quite a few or a bit fewer consumables, just due to the fact that the lamp is of such significant power. If we look at the graph here, it's kind of a blurry graph, but hopefully we can make this out. In the center where it says low pressure lamp, that's a single output at 254 nanometers. That's the solid line. So if we look at the dotted line, that's the medium pressure system, and that's the output from that lamp, peaks and valleys from 200 all the way up to 400 nanometers. One thing to put this into context, this was a lot of words. I like to associate this with the shotgun versus rifle approach. You have your, if you're familiar, you have your low pressure system, which I would call the rifle. right? That's your single bullet, that's your single target, a precision instrument looking to disinfect at 254 nanometers. Then you have your shotgun, which is your scatter blast. You know, you got the pattern of BBs. It's certainly going to hit right what's in the center at 254, but it's got a lot of other oomph behind it and a larger pattern to reach out and do more damage to different portions of the DNA, like we were talking about. So medium pressure versus low pressure applications in commercial aquatics, how does it make it different and what are we looking at? Medium pressure over here on the left-hand side. So I'm showing you guys our wafer UV systems. This is a premium medium pressure product. We have flow rates in this product range available from 250 GPM all the way up to 3,500 GPM. So suitable to large flow applications. We like to say this is best suited for indoor pools, high bather load applications, high combined chlorine applications due to the polychromatic output from the lamps. Outdoor pools, you know, they don't necessarily say UV is required, but we'll talk about that a little bit more. Medium pressure having a greater effect on combined chlorine and chloramines is suited well for outdoor competition pools as well, where there are bathers at that water to air interface. Low pressure systems on the right-hand side. This is our new barrier TEI system. This is a low pressure product range that handles flow rates from 50 GPM all the way up to 500 GPM. So we think this is best suited for disinfection only applications, you know, predominantly where we're looking just for that disinfection aspect of the UV output. This is great for outdoor features in pools. It's also great for indoor low bather load applications where combined chlorine maybe isn't that much of an issue. Talking about indoor versus outdoor water and air quality and the implications. Got another poll question coming up here. Haven't taught you much about indoor versus outdoor yet, but knowing what you do know now, where do you see a use for UV? Indoor, outdoor, both, none? Your poll should be live. That's good feedback here. I think the general consensus from the industry, you know, in my opinion, from my experience with it, is that UV is predominantly pushed in indoor applications. And a result of that is, you know, the way UV was really introduced into the United States aquatics market was for those tangible results that we can smell, that we can, you know, see. That was the combined chlorine reduction. And that really helped with the adoption of the UV systems in the aquatics market. Then crypto outbreaks happen, and we realize we can use these for disinfection as well. So there's multiple advantages. Go ahead and end the poll here, and I'm going to move on. So indoor versus outdoor application. Like we said, indoor, we're mainly focused on combined chlorine reduction. We need a higher dose in indoor applications, and that helps to reduce the combined chlorine faster while still providing sufficient UV dose for disinfection. Generally in these applications, again, due to the di and trichloramine species that can be present in the water, we're looking to utilize medium pressure UV. So in indoor applications, usually UV systems are running around 60 millijoules per centimeter squared. If we look over to the right, we're talking about outdoor installations. Predominantly, these are disinfection only applications. We have spray pads, spray features, we have fountains. Outdoor competition pools, like I said, they can also benefit from combined chlorine removal. So sometimes we look to medium pressure as a solution for outdoors as well. So we're saying both medium and low pressure systems should be considered for outdoor applications, depending on what they are. The disinfection dose generally is 40 millijoules per centimeter squared. That's the industry recognized minimum. And in all reality, you know, that dose is usually much higher than needed to produce, say, a 3-log reduction of cryptosporidium. So basically 40 is an all-encompassing dose that looks at inactivating different microorganisms in the water. and it can inactivate the vast majority at those levels. Let's talk about air quality. It's critical for swimmers and guests. You guys can see the graphic on the side here. We've got this air and water interface. In the water, you're free chlorines combining with your uric acid, your ammonia, urea in the water is creating different chloramine species. Those chloramines are volatile, so they interface, with the air-water interface, and they can off gas. So essentially, right at that, plane is what I would say the danger zone for our patrons that are in the water. Now, those continue to off gas, and the chloramines can go up into our environment and into the atmosphere in the natatorium and affect patrons that are sitting there watching, swimming, parents, whoever else is in the audience or wherever. Basically, once it's up there, it's not only the smells and the discomfort, but it also can affect different structural aspects of the building as well. So basically what this graph is saying, it affects both the air quality indoor and outdoor applications. And the stakeholders inside are your observers as well as your swimmers. Outdoor predominantly, we're talking about our swimmers. So combined chlorine in pools. Talk about that a little bit more in depth. So how they're created. Bathers in the pools introduce substances in the pool water such as urine, sweat, and skin cells. I have a transition here. Robin, I think you warned me about that. And now I am jumping ahead. Excuse me 1 second. So they introduce substances such as urine, sweat, skin cells, these contaminants. I don't know if anybody knows how to shut those off while we're live here before I keep playing with this. Give me 1 second here. I am sorry. Contaminants can contain high levels of uric acid, urea, and ammonia. So they basically react with chlorine to form several byproducts, notably chloramines. Chloramines cause the red eye, headaches, unpleasant odors, and skin irritation. They've also been linked to asthma. Chloramines can also be bad to the environment as well as they can be bad for health. So stress corrosion and cracking. In 1985, 12 people were killed in Uster, Switzerland. When the concrete roof of a swimming pool collapsed after only 13 years of use. The roof was basically supported by stainless steel rods in tension. They failed due to stress corrosion cracking. In 2001, ceiling of a pool in the Netherlands also, fell and crumbled due to the same reasons. Jump back there one more time. Chloramines are thought to be one of the 3 main factors in the corrosion of stainless steel in swimming pool environments. So disinfection of chlorine-resistant microorganisms, Cryptosporidium. Cryptosporidium is a protozoan parasite which causes cryptosporosis. Excuse me. I am really fighting this presentation here.
No
It's a form
worries.
of gastroenteritis. Yeah, it's a form of gastroenteritis causing nausea, diarrhea, vomiting, fever. The infections, usually they're pretty short, but they can last up to 4 weeks. Cryptosporidium, it can be treated by chlorine. All right. Historically, this was the way that this was gone about, but it only works at very high concentrations. So Cryptosporidium is protected by an outer shell that makes it very resistant to chlorine disinfection. So you kind of have to crack that shell before we can get inside and inactivate that microorganism so it can't reproduce. When your body absorbs this, its incubation period is usually 5 to 7 days after exposure. So unless you're aware of, say, a fecal incident in the water, you might not know, that you've actually been exposed uh, until this long after. Compounding that problem, young children, they can also carry the parasite asymptomatically. So, some of our most susceptible swimmers might not even show the symptoms of this. 1 gram of feces can contain about 1 million cysts of cryptosporidium, and it only takes 1 to actually cause the infection. So even if you don't have symptoms anymore, we shed crypto into the water or wherever else we're at 2 weeks after symptoms stop. And unfortunately, acute gastrointestinal episodes can reoccur 33% of the cases. So crypto is not a fun thing to deal with. And I'm looking for my slide that actually talks about that. I think I skipped over it here with the transition. Well, we got that. That's the one that skipped away. So recapping all of that, basically we're looking at inactivating cryptosporidium, whereas normally a chlorine tolerant microorganism, the UV disinfection can actually treat that and up to a single pass through a qualified UV system. So we're going to talk about that next. NSF certification and how it relates to the UV. So NSF 50, big buzzword in the aquatics industry. I'm sure everybody's familiar with it. Everybody's heard of it. NSF 50 can be seen as kind of a generic response. Oh my gosh, with these transitions. I don't want to rush through reading the material here. I'm just fighting this slide, so I apologize. I can talk to it either way if you guys cannot see it here. So NSF 50, as it applies to UV systems, is much different than how it would apply to, say, filter or a pump or a main drain cover or anything else that's applicable in the aquatic space. Essentially, NSF, as it applies to UV, has a couple different levels of testing. First and foremost, we want to make sure that the materials that it's constructed out of are not toxic. They're not going to leach anything toxic into the water. So, okay, we have NSF 50. Our materials of construction aren't going to hurt anybody, hopefully. Now, that's not really speaking to the disinfection or the performance potential of the system. That's just saying what it's built out of is safe. 2 other standards for UV disinfection as it relates to NSF 50. And the first is what we call supplemental disinfection. So supplemental disinfection is a specific test from NSF 50 that basically tests for the inactivation of a couple different bacterias, not cryptosporidium. And what's odd about this test is the fact that we are able to inject the water so we can test the performance of the system, but we allow that water to circulate through the UV system up to 6 times. So essentially, we're given 6 chances to do the work to inactivate the Enterococcus faecium or Pseudomonas. And basically what we're trying to achieve there is a 99.9% reduction. But again, we get 6 chances to do it. Let's skip ahead here now. Secondary disinfection is the other. Yeah, let me try to back up if I can. Secondary disinfection is the second test. So this is an updated test standard through NSF 50. And essentially what we're doing here is we're testing for the inactivation of cryptosporidium. So specifically cryptosporidium in this case. And the pass-fail criteria is you must achieve a 3 log or a 99.9% reduction of cryptosporidium specifically in a single pass through the reactor. So we're talking full flow, 1 pass, 1 chance, pass-fail. This is much, much different than supplemental disinfection. It's much more difficult to pass as well. So xylem ETS UV, Neptune Benson. We recommend qualification under the secondary disinfection standard as the preferred UV system qualification rather than supplemental disinfection. Again, one's talking about crypto reduction, one is not. One is more stringent than the other, one is not. Second here, I think I've figured out a trick to beat the system finally. No. So just some points to consider around NSF. Recommendation is always to consider a UV system that's rated for secondary disinfection, not just supplemental disinfection. You want to view a manufacturer's claims on the website, nsf.org. When you go into any manufacturer, they should be listed for UV. And essentially this graphic here is kind of small, but if you see on the right side, we have a listing of applicable model names. Their maximum flow rates are in the second column, and whether they are listed for supplemental or secondary or both. So you can easily gather all of this information for any manufacturer's UV system right on the website itself. One of the other things that goes hand in hand with NSF 50 certification, it's not enough to pass the test there. We have to monitor that we are doing the work in the real world. So we have to have validated UV dose monitoring systems so operators and regulators can validate the system on site at a glance. Essentially UV systems that have a on-off light, pass-fail, yes or no, the lamp's on, no, it's not. They're not necessarily telling us the intensity from the system. They're not necessarily telling us the perceived UV dose that we're applying to the water. So if that's of concern, which it certainly should be if we're investing into this type of equipment, we want to make sure that it is guaranteed to monitor and tell us it can do what it says it's going to do. Got a poll question here. Were you aware of the different NSF test standards? Right. That's good. I mean, essentially that's the point here, is to try to educate everybody on what's out there. One of the biggest things with NSF standards, as I said, it's kind of an all-encompassing generic term. I've got NSF 50. That's all you got to say. But what does NSF 50 do for us if it doesn't prove that we can do the work in the water? Yes, our materials are non-toxic, but is the light on? That very basic standard doesn't ask that question. So essentially we look to the standards to understand them, to see exactly how efficient the UV system is going to operate and what it is capable of. We have another question here. Do you know if your state requires NSF 50 for UV? I'm launching the poll right now. Interesting. Yeah, a lot of yeses. As these regulations become more and more prevalent, they get adopted in more and more locations that are looking for guidance and looking for that assurance that their code is protected by testing of equipment. Got a case study I want to show. So UV disinfection solution protects bathers from cryptosporidium. So one of the main things that we're talking about here, we got a water park up in northern Minnesota. Let me see if I can figure this. Yeah, pause here. I'm going to lose this slide again. Here we go. A water park up in northern Minnesota. Basically, they invested in ETS UV disinfection systems in a response to a crypto outbreak. And they basically wanted to improve water quality and protect bathers. So the customer was Edgewater Resort and Water Park in Duluth, Minnesota. And the resort water features included, they had an outdoor pool, they had a hot tub, indoor water park with 3 pools and a hot tub. The main challenge here was restoring the faith of the public health to protect the patrons against future crypto outbreaks. The key to success, we utilized UV disinfection as it's 99.9% effective at inactivating crypto in a way that normal levels of chlorine will not. And the solution was ETS UV. So we've got a talking point from the Director of Applications, Hannah Jansen here, basically saying the results we experienced were astronomical. Our combined chlorine's been nearly eliminated. Our chemical readings have been right on, and our equipment's lasting longer. Installing ETS disinfection was the best thing we could have done to improve our facility. And this story is the same at many locations. Essentially, that's what we have for presentation material. I want to apologize for the slide deck malfunctioning and acting up on me. So I understand if there's questions around any of those points where you're probably distracted by me clicking around, and I'm happy to answer those or any others that you may have. But the floor is everyone's here, and I totally encourage any questions or feedback.
Thank you so much for that, Greg. I have 2 questions here that we can start with. The first being, does UV destroy free chlorine too?
Sure. Yeah, that's a good question. So UV is indiscriminate against breaking down its chemical bonds when it comes to free versus combined chlorine. So essentially, when it's in the water, we size systems appropriately so that they're going to attack the combined chlorine first. And if there is not enough power left in the system, we should remain static at that point and leaving the majority of the free chlorine residual in the water. So as we go through validations and certifications like NSF 50, we do that not only to prove that we can do the work when it comes to, say, inactivating cryptosporidium, but also we gather a lot of important data from those tests that allows us to size our systems accurately and not just throw the biggest system at the water that we possibly can. I would say free chlorine has the ability to be reduced more so in applications where the UV is grossly oversized. You know, we're kind of counting on these applications to keep producing the chloramines in the water, and we're going to keep working on them. It's kind of an equal give and take, right? We have all the ingredients in the water, the free chlorine and the swimmers, and we're going to keep making chloramine, and we're going to have a UV that's adequately sized to take them out at that same pace.
Mm-hmm. Thank you. One other one that I received was, how often do you need to replace the lamps?
Sure. Yeah, so that's a good question. In comparison to both systems, we talked about low pressure versus medium pressure systems, and lifespans are generally different between those. Low pressure systems have a longer lifespan, usually around 12 to 16,000 hours, depending on the manufacturer. And medium pressure systems, depending on the manufacturer, between 6 to 10,000 hours, usually 8 to 10,000 hours. Things that can definitely affect lamp life are on and off cycles. In the commercial aquatics applications, we don't generally see the systems being turned on and off often. Usually only when we go to backwash our filters and we remove the flow from the systems do we shut them off. So considering 1 on and off cycle per day, those are the timelines for lamp replacement generally.
Great, thank you.
Mm-hmm.
If anyone has any other questions that they want to you feel free to unmute and you can, pose them verbally, or if you prefer, you can throw them into the chat. And I'm happy to read those aloud. I know somebody did ask about the recording. Yes, it has been recorded and it will go out later today as well. So, you'll be able to, rewatch this and go back to, rewatch anything that you need to.
I have a question.
Sure.
Absolutely.
Our pool is a smaller indoor swim school, about 20,000 gallons. Our flow rate is around 60 or 70 GPM. In a course, the CPO course that we took, our textbook says UV systems are superior at destroying inorganic chloramines, but doesn't really sell the point about destroying organic chloramines. Is this something that's like the mono or dichloramine? Is that where the difference is?
I would interpret that as, possibly that if it's asking, is it differentiating based off of the type of UV system? I mean, does the CPO course indicate low versus medium pressure? And that could be that could be the argument there, right? And as we said, low pressure, they do. We're not going to say that they don't reduce combined chlorine, but usually only the monochloramines. So if we think about this too, monochloramines can form from free chlorine, and they can form from uric acid in the water in combination with that. The way that we get di and trichloramines is from monochloramine. So essentially, your low pressure UV system can control the chloramines in your body of water, provided it controls 100% of your monochloramine before they get a chance to turn into di and trichloramines.
And if
whereas
we've been in place for years and we're struggling to control our chloramines, is there anything we can guess at why it doesn't help in control?
Sure. Yeah, struggling to control them with UV, I assume, is what the question was. Yeah, a lot of different things to look at. Whether it's the, start with the obvious, the maintenance records and the parts age of the system. But then we look into, other things such as the loading of the total chlorine that's in the water. Where are we running our free chlorine at? Where are we running our, how high our combined's getting? Something that's counterintuitive, in the industry, a lot of people want to run the free chlorine as high as possible to maintain that level of residual safety. But in all reality, the higher we run the chlorine, the lower the UVT can actually be in the water. That can inhibit the amount of light that passes through the water. And it also is basically like, I would say, doubling a batch of cookies or doubling the recipe for a batch of cookies. If we put that much more free chlorine in the water and we have that many more bathers in the water, we have the ingredients available to make that much more chloramine. So when we limit our free chlorine down to, residual levels that the state mandates, it can be beneficial to lowering chloramines overall. And that has less work for the UV system to actually do. Apart from those 2 points, just looking at the water quality itself, we talked about UV transmittance. A lot of times in very high bather load applications, this can be a significant drop. But a lot of systems are sized for, higher than 60 GPM on the market. So if that's the case too, a higher sized system should be able to accommodate lower transmittance levels in the water. Yeah, there's a lot of different things to look at.
Okay, thank you.
No problem.
Thanks so much, Greg.
Yeah.
Anybody else? Any questions? Kind of your last chance, and if not, we'll wrap up here. And Greg's got his email listed, so you can also reach out to him directly. To chat further, get any questions answered that may come up later. I know sometimes that happens. So, if not for right now, I think we will wrap up today. Thank you, particularly Greg, for joining us today. And I know obviously everybody got a lot out of this, based even on the polling questions. We certainly saw that. So thank you. And thank you to Robin for your support on this, and all of our members for joining us today. We really appreciate it and hope everybody has a wonderful rest of your day.
Thank you, everyone.
Thanks. Take care.